Thanks very much for coming along. Today I'm going to talk about some work that Rohit Chandra, who's now at UNSW in the Maths and Stats group, and I did together with Dietmar Müller, who's in geophysics, and Nathan Butterworth, who is in SIH, I believe, but he works a lot with the geophysics guys, did on trying to have a look at precipitation going back 250 million years, using sort of data fusion techniques that tries to take into account lots of different sources in order to try and understand what our climate might have been like 250 million years ago. Okay, so that was the broad aim. As I've said here, so the goal is to really try and fuse information that's available from a number of sources, so sediment records, models of plate tectonics. That's one of the areas of expertise that Dietmar Müller and the group do in geosciences. They have models for how plate tectonics have moved over time, and that's clearly going to shape climates because of continents grouping together or being far apart, and how much sea goes in between continents is all very important for climate. There are reconstructed paleo elevation maps, so how high the planet, various parts of the planets were. And then a couple of high resolution, what's now I can say GCMs and actually know what they mean, which are global
General circulation.
General circulation models, not global climate models. Okay, general circulation models. Thanks, Nandini. To improve our understanding of precipitation. So the first type of information that we have, so there's very many different types of information. Some of it objective, most of it not. So when we started this work, I didn't realize that this, what I've now come to call as models as data. I actually thought that they had data on rainfall back in the 14 million years ago, but they don't. These are rainfall from general circulation models and not from they had no rain gauges back then, which we happened to tap into. So the sediment records, they have three different types of sediments that they've sort of recorded and the age of those things. So the first type is coal, and what you see here is just an example of, this is 14 million years ago. These is the probability here of coal being found anywhere. That's one of the outputs of the work that we did. But we just start off with these areas where coal was found and dated back to about 14 million years ago. That was one type of deposit, and obviously the idea being that coal is usually associated with more wet climates than drier climates. The other type of deposit, which I'll get to, well, I'll show you some graphs, but was evaporites. So evaporites occur where places are dry, right? So things that they have are things that are available are these sediment deposits. These sediment deposits do not cause precipitation. They are a function of precipitation. But what we're going to try and do is use precipitation from only a very small time period, together with sediment information that goes back a long way, to try and figure out what rainfall might have been based on the sediments that were found and dated back to various eras. So that's the first piece of information. The second piece of information, and I want to thank the Earthbite group, of which Rohit is a member, and which is run basically by Dietmar Müller. These are the plate tectonics. So here you see this big mass. This is, I believe, I'm not an expert on plate tectonics, but this is Pangea. You can see all the continents are all squished together. And as they, it was very dry back, 250 million years ago. And as you see them moving apart now, particularly about now, you can see that belt at the equator of sea water gave rise to a lot more rainfall and various, but there's India coming up. It's about to connect with Asia.
Sorry, do you have a rainfall indicator on this?
No,
okay.
this is just these arrows are just the these are not rainfall, these are just the way the plates have moved. Now, this clearly has a huge implication because, you know, an island gets a lot more rainfall than something that's far inland. You know, depending upon which side of a continent you're on, also depends upon, you know, influences rainfall. So there's a whole range of reasons why plate tectonics are important in and of themselves. And they're also important for us because, you know, the sediments are found on a particular plate. So knowing how that sediment is not the sediment that was found somewhere, you know, 200 million years ago will not be at the same location, you know, 100 million years ago, because it will have moved as a result of plate tectonics. Then they also have...
Quick question there, do these tectonic maps over time have uncertainty associated with them, or they're pretty sure?
No, they all have uncertainty, but unfortunately there's just very little way of knowing what the uncertainty levels truly are all the way back there. Yeah. But these, these three sources of information all have must have a lot of uncertainty. But at the time, we didn't really know. I thought that somebody actually knew that the plates moved. I think they're pretty confident, but no, these would have uncertainty associated with them.
And with the motion of the plates, it's always, I'm not sure how they exactly derive that. But
there'd be a lot of interest in things I know nothing about. So I'm going to try and answer it, but I don't know that I will.
No, I just kind of wonder whether I know that some of it came from looking at plants, the different places around the world. That's kind of
from what I understand the plate tectonics, a lot of it is that they were able to see on the ocean floor these tracks of magnetic fields that only could have given rise. The interesting thing about plate tectonics is prior to 1950s, we had no idea. We didn't even know that there were these things like plates floating around and shifting. So it was a huge boon in our understanding of what our Earth had looked like in the past once we actually got this idea of, but they are just a theory of plate, you know, so plate tectonics, but it's pretty based on, it's based on a lot of, well, various sorts of evidence.
So I guess if you build this spatial-temporal model of precipitation, it would be very important to georeference these sediment records back in time.
Yes, yes, exactly. So yes, so you've got to take into account that the sediment records, yes,
are shifting.
Yep. So yep, they are, and that they belong to a particular plate. Yep.
But just seeing this map, it seems as if we have a principle of conservation of continents. Continents don't go underwater and they don't come out of water, but they only shift.
I think that they do come out and underwater. Which is, you can see from the size of the continental shelf around the outside. But yes, it is small by comparison to what stays the same. So these are the actual plates, though. I wish I knew everybody would be interested in this. But these are the plates. So the plates are not the continents. The plates and the continents are not the same thing, right? So these blue things are the plates, and you can see, here's one big mass is Australia. They were all together in one big plate, and then things started breaking up. I think you'll see, hopefully. About now they start breaking up. Yeah, you can see the breaks coming in there. And that's Australia's becoming, it's sort of there with India. Now India has its own piece. And as we know now, Australia is shifting north. India shifts north at a bit faster rate than we did. It's going to collide with Asia, forming the Himalayas very shortly. There it goes. And that's sort of what we know from today. That's our plates from today. I know. I just, every time I see these talks by the geophysicists, they have such cool stuff. And, we've only got equations. Anyway. The other thing that they have, and again, this is, there would be uncertainty associated with this, only that I don't know what that uncertainty is. At the time, I actually thought that they knew, but they don't, so which is fine. But this is going all the way from 242 million years ago right to now. And this is just giving you elevations. It looks, and the reason that elevation, I'm sure you appreciate, is in the model is because it's a big predictor. Well, it's a big influencer of rainfall patterns. Okay, so so that's the elevation maps. So in effect, these things are trying to take in the physics of things like plate tectonics, and in this case, landscape formation, but not by actually embedding, probabilistic things within the physics of it, which is actually where we should sort of be thinking of going, but more by just taking the output of them and using that to try and form models. So in that way, we're incorporating what is known by the physics without actually knowing or understanding what the physics actually is. But it would be good to really actually understand the physics and to somehow embed probabilistic models within that. And then the high resolution general circulation models. Great, got it right. The last one that are important. So apparently these models take months to run to get output from these models for going back. This is 14 million years, and this one's about 38 million years ago. And these are the precipitation that they had for these time periods. As of when this was done, there's been no really GCMs that have gone back, 200. They haven't got precipitation for GCMs going back 250 million years. That would be another way of getting a handle on what precipitation was. What our technique does is take the output from this and use the output from these together with this relationship between the precipitation here and these things, and then project that back in time so we get an idea of what was happening 250 million years ago. Probabilistically, yeah. We do that part probabilistically.
She said mainly due to CO2 records or something like that? Or?
So CO, I imagine all the CO2 records would have been embedded in these GCMs. Which
Yes,
right
they have estimates of CO2 going back, and so they would have put that in. But also the continents were very slightly different. So if you look at these maps, you can see the gaps between different continents were a bit different. So there was one where there was some period when the Panama Strait was open. There was some period when Torres to
the south.
Yeah, there was one period when during glacial periods, so ice ages, all the water was sitting on the land in the form of ice. So your sea level actually really dropped, and everything from northern Australia to like Thailand was land. And those things really changed the ocean circulation. And so those are the sorts of changes that are inputs to the GCM to produce this precip.
Yeah, I mean, they're incredibly complex models, these GCMs. So they're sort of like a digital twin of the whole world. You've heard that digital twin comment in engineering. They want to build digital twins. Basically, GCMs are digital twins of the history of the Earth. So they're very complex things. Okay, so this is just summarizing, what the data structure, I suppose, looked like here as the millions of years ago that correspond to the different ages that we wish to predict. These are the number of observations, and I say observations loosely, that we have for each one of these eras. These are observations for which we have things like the elevation, what you'll see later on. We use those plate tectonics to get estimates of the distance to shore, of the angle that the closest distance to shore is, to tell us about the orientation of the continent, whether it's on the east or west side of the continent. So these are things that we've got for sort of spatial features. These are the number of sites where we actually have we know something about the sediments that were found there. This is divided up into 5-degree grids, I think, across the planet. And these are, as you can see, you know, the sediment coverage, you know, drops off as we go back, and it's very sparse by comparison, you know, sort of like, you know, less than well, what's it? You know, it is, you know, very sort of 73 as opposed to 1500. So we've got a lot of missing sediment data that needs to be imputed, not imputed, but integrated over in order to take account of the uncertainty that we don't have that information. And that's the way that the sediments are broken out. You know, here's coal, here's the evaporites, and there's not many glacial ones back in the past. In fact, there's hardly any glacial ones at all. Right, so that's the sort of data. So what they really were interested in was in, you know, predicting the precipitation, or at least understanding the predictive distribution of the precipitation, using all the available data, and I'll talk about how we're going to define the data later on. But effectively, they're interested in this joint distribution. They were interested in the joint distribution of sediment or deposits and the precipitation. And, you know, just breaking that down, you know, this is the distribution of the sediments conditional on the data times the, you know, distribution of the precipitation conditional on the sediments in the data, right? So the idea is to construct a model which models these two things here. So we've got to construct models that marginalize over precipitation effectively here to just get the marginal of sediments given the data, and the I don't know what I did. Oh, right. Okay. Okay, so just to define a few things. These are, so here, you know, obviously these are, you know, random variables, but, you know, we have realized values of some of these random variables, which we've denoted by observed. So for each time period, so Z is this array. The array consists of capital T, which is the number of time periods matrices, where each one of those capital T matrices consists of whether or not an observation was recorded at location 1 to NT and at site S. So effectively, that's what the deposit data is. Okay, and so it was just a dummy variable that took the value of 1 if a deposit of type D was observed and 0 otherwise. Right? Okay, so you've got this grid, and you've either observed things or you haven't observed things. Most of the time, in most of those grids, so for example, in the 250 million years ago, there were 1500s or thereabouts of those cells. Only 73 of them we actually had information on deposits. The vast majority, the cells, we have no idea what was actually there or not there because it wasn't sampled. And what they tend to do, and we didn't take this into account either, but if they get a sample and they find that that's a sediment that belongs to that era, and they find something, then they go and, you know, search all around that area for more. So you're more likely to, so it's not, things unfortunately are not missing at random, but we've assumed they are missing at random, but they're most definitely not missing at random. Okay, so precipitation, the same idea. The precipitation is just the, this is just a matrix of precipitation where Y S of T is the precipitation at site S in the era T. And it's the annual precipitation. And then for all these sites, we know things like latitude, elevation, distance to shore, and the orientation to the nearest shoreline, which effectively is the coastline. So it's sort of trying to pick up the orientation of the site with respect to the east or west coastline of the nearest coastline. So they are the data definitions. So we're going to be dealing with Z's, Y's, and X's. you know, so just before we get into anything mildly sophisticated, just a sanity check, you know, these are what you should always do, as everybody here knows, is have a look at the data before you start your modelling thing, and just have a look at how precipitation is related to these various bits and pieces. And you can see it's very noisy because there's an awful lot more going on than just distance to shore or the elevation. And these are just for the 2 time periods that we actually observe precipitation, or rather we had the GCM output for precipitation for those time periods. Just looking at those spatial characteristics. Okay. Okay, so now we have a model. We want a model that's going to just model the probability of finding a particular type of deposit given all our data. And we're going to do this, not surprisingly, you know, so we have those data, as I'll go back to an example of them. You know, we basically, we want to be able, here are our observations, and we want to be able to infer, or we want a model for predicting the probability, as this model does. You know, this is an output of that, of finding coal at any one of those groups, conditional only on those data. So we have to, you know, and obviously what we're going to do here is use a GP, you know, to predict across areas where we don't have any observed sediments, using basically a probit style regression, and I'll explain that in a little while. So, okay, so where to begin with this? Okay, so this is just what we are going to do is to model the probability that you're going to find a particular deposit at a certain location in a certain era. And we're going to say that this is just, well, let's talk about the ring function in a little bit, but we're going to model it as having a linear component and a non-linear component. So this is like the mean of a GP, and this is a series of basis functions that are constructed from the GP. So I'm sure Roman talked to you about basis functions, and one way of constructing basis functions, you know, what does a GP assume? It assumes that the function estimate at a particular location is related to the function estimate, or the covariance of between 2 locations is stronger the closer the locations are, and moves away further as you get apart. Now, whichever one, there are many choices to use in GPs, and we just chose a 2-dimensional thin plate GP, and this is the reproducible kernel in Hilbert space. That's our covariance matrix, and that changes for each time period, and that we've just decomposed that covariance matrix into doing an eigenvalue decomposition of it, and we get sort of computational efficiency by, well, we just truncate off. You know, we just take the top, in this case, 60 basis functions, although it shouldn't overfit even if we took all of them, but it's just computationally intensive if we do take all of them. And if we can do this, this eigenvalue decomposition, and we can define this design matrix here, W, by it's equal to the eigen matrix of eigenvectors, eigenvalues times the matrix of eigenvectors to the power of a half. The reason that we do that is that we then decide these regression coefficients have this normal distribution, and then WT times these regression coefficients is approximately equal to, is distributed according to this GP, right? So that's the whole point of doing it. If you take the covariance of W times phi, you'll get that it is in fact 4 squared times omega. So now you have just taken a covariance matrix and just doing a little trick, you've turned it into a linear regression problem. And I'm sure you've all seen this and seen that done before. Okay, so that's, and this is just the mean function. So the mean function It's just a linear component of both latitude and longitude. So we're doing this for each era to try and get a prediction or to average over the locations where we actually don't have any sediment information. And this phi, we're going to, or psi, is going to be the is our link function. You know, there is, you know, you could use any CDF here, right? You could use, if you use a logistic CDF, we call it logistic regression. If you use a standard normal, this is called a probit regression, but actually any CDF will take something on the real number line and map it to the interval 0, 1. So anything of that nature is going to be okay to use as a link function. Now, the reason that we use the standard normal CDF is that, you know, using a small trick in data augmentation in Bayesian sort of methodology, we managed to turn this binary regression problem into a Gaussian regression problem. And that becomes then very easy for us to deal with. So basically what we're going to do is define some latent variables that have a normal distribution and generate them each time through the MC scheme, because conditional on them, we can then compute this, this function and then average over all those possible realizations of those latent normal random variables. So that just is a way to make things computationally efficient. Okay, so the second part was to get a model for the precipitation. Given that we observe the sediments and some spatial characteristics. Here is just pretty much a straightforward regression with all the components added in there, with the exception of there's two things, I suppose, that are different here. So we're adding now, which we didn't for the sediments, we're adding in all sorts of things like distance to shore, elevation, all those bits and pieces. In addition, because now we know the sediment deposit, so the Zs, so each time through the MCMC scheme, we use it to generate a realization of the missing Zs, and then use that in the model that updates the precipitation. And we're integrating over that through each iteration of the MCMC scheme. Here we have, so we do know that actually that latitude plays an awfully big role in precipitation. Here's precipitation versus latitude for 14 million years ago, and this is the same one for 38 million years ago. There's a reference in the paper that says basically the relationship between latitude and precipitation hasn't really changed for the last 300 million years. So we've assumed that that sort of relationship is constant throughout. And you can see, obviously, you see the peak at the equator, where there's the most precipitation, followed by these dips, which are usually associated with the mid-latitudes and the deserts, and then followed by slightly wetter climates further outside those mid-latitudes. I don't know if you can see it there, but the blues are missing observations, so they're all the sediments that we haven't got. And then the other ones where we do observe sediments have been color-coded, black for coal and red for evaporites. And there's one tiny one there for glacier. So you can see that the coal is associated with a high rainfall. So
why is GP suitable here for precipitation? Given that it's not the normal, typically a normal multi-discipline function.
Okay, so we had a GP with the binary stuff, and that wasn't normal, right? That's zeros or ones.
Yeah, you can marginalize.
Well, then we are averaging over. Here, this is actually the cube root of precipitation. In a lot of the rainfall modelling, you can show that, and people don't know why, but the cube root is almost always very close to a Gaussian. So this is just transformed, so it's approximately Gaussian. Yeah. But you can see that we do need a GP here because it's not some known polynomial or some known parametric form. You know, it's obviously non-parametric, so we have to take into account that that functional form. So here's our GP. we formed our matrices, and we can, here is our coefficients of these spatial characteristics, I suppose. Notice that latitude and longitude is not in the model at all, because the longitude really has no meaning in terms of precipitation. Longitude will only really impact precipitation because being at a certain longitude will tell you whether you're on, a mountain ridge, or whether you are close to the shore or further inland, and it will tell you about the distance from, whether you're on the east or west side of a continent, because there's nothing per se about longitude that actually says something about. And if we put longitude in, you get very strange artifacts. You'd be picking up the continental movement without, which we don't want to make that. We want to pick up continental movement in terms of, what's the elevation at a certain location and what's the distance at shore and all those sorts of things. But we don't want to take longitude for one period and think that longitude in one period will behave the same way as rainfall as longitude in a different period where it may be a different continental plate underneath and all those sorts of things. So having done all that, we've basically just broken it up. The model for rainfall is just a straight signal plus noise model. There it is here. The H is just a concatenation of the matrices that have regression coefficients beta, and these are all entered in the linear function. And this is the non-linear part. So here, this L and delta play the same role as W and phi on the previous slide. In other words, we have a different covariance matrix. We do the eigenvalue decomposition, etc., etc. And so that we can write the product of that matrix times the regression coefficients as a GP. So that's all that is. Okay, so they were the expressions for the sort of likelihood functions, if you like. Here's the full model. So this says that a precipitation conditional on all these bits and pieces here is normally distributed with independent errors. We put a prior over the regression coefficients. These are the linear regression coefficients. These are the non-linear regression coefficients. So these are the things that, when they're multiplied by L, give me that covariance kernel. So this lambda here is a parameter, it's a hyperparameter of the GP. It controls how wiggly or smooth things are. This is the model for finding deposits, right? So each one of these is a Bernoulli random variable with a certain probability of occurrence given by, now I've changed it from psi to capital phi, but it is the same as the sign on the previous slide. It's just my slipping up notation. Okay, and again, this is decomposed into a linear and a non-linear component. And then we put a folded Cauchy prior over, or we put normal priors on regression coefficients, and we put folded Cauchy priors over the variance parameters, because there's been a lot of work done in that about showing that these folded Cauchy priors are indeed, are not as sensitive. The inverse gamma shrinking things too much to zero. And here is a graphical model if you prefer to think about things graphically. We've got here are our matrix and the coefficients of spatial characteristics. They feed in to give us our Zs. I would just note here that this Z with a S1 and S0, did I put it on the previous one? No. Okay. What ZS1 and ZS0 are is these are the set of Zs for which there are observations. So that's for which at least one of those coefficient, one of those Zs was 1, and these are the Zs that we are imputing as part of the MCM scheme for which there are no observations. Okay. Oh no, no, I don't even put it here. Hang on. Okay, so I haven't written down here. I have a lot more written down. Hang on, why isn't it? Okay. So what we want, if I could go back to here, what we want is this predictive distribution, right? We want the predictive distribution of Z and Y conditional on the data. And in order to do that, we're going to have to marginalize over all our unknown parameters. And all our unknown parameters are those things that we've just put up in the next two slides. So there are our hyperparameters. So we're going to have to marginalize over the regression coefficients, the hyperparameters of the GP, et cetera, et cetera. So if I can just get a pen and say what we really want is this P of Z and Y in the data. This is a slide I thought I actually had. And that's sort of P of Z, Y data, and so data, given the data. The students, of course, you all know that this can be approximated by a sum of Z and Y given the data, and theta J, say, where theta J is a draw from the posterior distribution of theta, right? So this is what we want to do, and this is what we need to construct an MCMC scheme to do. Right, so now I can go to that. So we're going to construct an MCMC scheme to do that marginalization.
I need to press the trash.
You can press the trash, Sally. Yeah.
So this is our vector of parameters. That these are all the collection of the alphas, the z's, the missing z's, or we just treat as parameters. So these are the deposits that we haven't observed. This is the noise of the variance or the error of the precipitation equation. This capital T is a vector or a matrix which is diagonal, and on the diagonals are all the smoothing parameters for the deposit. The deposit GP, and the lambdas are the smoothing parameters for the, the lambdas are the smoothing parameters for the latitude versus precipitation GP. And we do this trick, and I actually talked a bit about it in class, if you remember. There was, so basically we introduced these random variables where we have, we have that probability, we have the probability that Z, say, is equal to 1, given some covariance X is, phi of, say, X beta. And then we introduce these values here, these V, we say V is equal to X beta plus an E, and E is in 0, 1. And if we do this, we can show that the probability that Z is equal to 1 is actually equal to the probability that E is less than X beta, which is equal to phi of X beta, because E is in 0, 1. And so now we have a way which, if we generate these latent variables, these V's, if we know beta and we generate them according to this, but constrain them so that V, the unconstrained V, so here V is normal X beta 1. V given Z is normal with a constraint where the constraint is going to depend on the value of Z, right? So this is X beta 1. If Z is equal to 1, then C is positive, right? We're constraining it to be positive, and if Z is equal to 0, then we constrain to be negative. Now, why should we do this? Why is that important? It's just because having generated the V's according to this equation, then the sampling scheme is just a sampling scheme for sampling a normal GP with normal random variables, and all the standard things that we do about that just come into play, right? So you generate the V's conditional on the Z's and everything else, and then conditional on those V's, it's as though you're dealing with Gaussian data. And that makes it very straightforward. So here, so we go through one sweep, we generate all the missing Z's, we take those missing Z's, and then we generate the coefficients that describe the precipitation equation. Let's do that. And this is what, for example, we end up with. So I've got these for all of the deposits, but I've just put them up. So here is how the world has sort of changed. You can see it's a very different world from what it was 250 million years ago. And here is the results for the probability that we're going to find coal in there. But of course, we really just wanted this because we want to ultimately get to precipitation. Okay, so these were the results of coal, and we also, the paper has the results for evaporites as well as for glacial. Although there were so few observations in glacial, it's probably not really. The reliability is low. And I just hope this works too. That's okay. So here is, and this one sort of goes back. It starts off now and it goes further back in time rather than the other way around. So these are what the precipitation. Is it changing? It's not a very good resolution, but as it's going back in time, you can see actually the precipitation is getting less because we've got this big landmass. I'll talk a bit about that. So that's so just to sort of discuss some of the results, what they were interested in finding.
Okay, so the number of deposits is identical for all of them, right? Or is,
yeah.
Okay.
So for evaporites, coal, and glacial.
I mean, over time. So
yes, it changes over time. Yeah. So that's what that previous thing. I just didn't have a moving movie of that previous thing. You saw that it changed. Those probabilities changed over time. I mean, I'll just go back. So on there, these are not. This is the probability of finding coal, for example. And you can see that, you had much more probability, interestingly, of finding it at the poles, which I'll come to in a minute. So hang on. Okay. So the Triassic period, which is the earliest period that we looked at, has had one of the driest climates in the last 500 million years. That was done. That's been noted in an ad hoc way by a number of people who've done some work in the area. So basically what happened, why was it dry a long time ago? Well, because we were just all one big landmass effectively. And we had certainly here around the equator, you're getting more rain than at the extremes, but really, the vast majority of it is just one big landmass, which leads to less rainfall because you've got less coastal lines and less influence of the ocean. So as the second one said, so the spatial extent of the humid equatorial belt changed quite a lot. And as you can see, a lot of the evaporites here, if you look at the precipitation, this is low precipitation. So, and here you can see these are the probability of evaporites. You see you're getting high probability of evaporites at those low precipitations and everything like that. So that's the Triassic period. And then, of course, things started to break up. And this was the Cretaceous period. It sort of began about 150 million years ago. And it's thought that there has been a single GCM done that suggests that it was that rainfall or precipitation was approximately 10% greater. And you can see that a pattern of pronounced low latitude rainfall, especially in areas that are deserts today. So this is the top of Africa a long time ago, and that had a lot of rainfall. It was around about the about 150 million years ago. What you can notice, the reason that the rainfall has now increased is because Pangaea has expanded, and you've got this channel that's going through the centre that wasn't there before, leading to more rainfall in the equatorial regions. And that's what this says. So relatively wet North Africa and Southeast Asia to what we have seen today. And lastly, so what are the features of the Cenozoic era? Well, you've still got that presence of this equatorial seaway, and you can see still though at things like 61 million years ago, you still had a very wet Northern Africa. But what you can see is that Northern Africa is slowly shifting up northward, and it's shifting up into so it's gone from here where it's all wet, and then now it's in that area where it's suddenly desert. Well, not suddenly desert, but it's very dry, which is much more consistent with what we see now. So this is only 14 million years ago, of these very dry, arid regions, which were once very wet in the past as a result of their latitude, essentially, a major. What you've also got here, I think you can see here, is the emergence of these ice sheets at the bottom, and that was associated with global cooling. Basically what you've got is the continuing dispersal of the continents following the breakup of Pangaea. Okay, so I think, thank you. Questions, please. Questions to do with data science, not Paleolithic